Yeah, thanks.
Okay, I think we can get started. The the last session for today. So our speaker is Sergej Flach from the Center of Theoretical Physics of Complex Systems in Daejeon, South Korea. So we look forward to your talk.
Yeah, thank you. And thanks to the organizers for the invitation. It's nice to be back to Bangalore. Last time I was here shortly before the pandemic hit, end of 2019. And there I reported on work which is related to what I'm going to talk here today. And some of the people whom you see here were involved in the work I reported 4 years ago. And this whole story about thermalization started with the work together with David Campbell and Carlo Danieli, and then others joined. Mithun, Jagmur, Alexander, Thomas, Michael, Boris. I'll not say that one for a reason. You'll see that one not. Emil Yushbashian, and that one not. And Aniket Mitra, because the work I will present today was done by these, together with these 4 colleagues. And yeah, they again slightly reshuffled. The main work was done so far by Mirab Maleshava and reported and published. He was a PhD student with us and is now working in a company in Seoul. Weihua Zhang is a long-term PhD at, how should I say that, student trainee or student on an exchange student coming from China and working with us for the 2nd year. Gabriel is a recent hire into our center, and Barbara is a senior member of our center as well. So I will try to tell you about our new results on thermalization dynamics slowing down. What we are interested in is how a many-body system will slow down its thermalization upon approaching an integrable limit by tuning some parameter. Now, disclaimer, I will talk here only about classical systems, that is nonlinear systems, but I'm happy to do philosophical aftermath discussions about what will happen if we quantize these systems. The goal is then to find whether there is anything interesting, except that there must be, of course, some slowing down. Are there different classes of systems which will slow down in different ways? How do we quantify actually this thermalization process? And are there maybe therefore novel dynamical regimes of this thermalization close to integrable limits? I'll talk, of course, about finite systems because I will show you results of computer simulations. But ideally, we want to map this, our understanding, onto really macroscopic systems. I will talk only about microcanonical dynamics, but you will see in what sense, because I will here talk about maps, because this is a meeting on driven systems. And it so happens that we do have results, in particular on that for such systems. If I pick a typical such system, it will be non-integrable, and still I can maybe find ways to tune parameters to bring it close to integrable limits. By integrable limits, and in particular when it comes to maps, to periodic systems, what I still mean is that there's a proliferating number of conserved quantities, conservation laws, and if you allow me to call these things also maybe map actions in analogy with Hamiltonian dynamics. So typically these non-integrable systems are expected to be good because they should at least conserve one quantity which has a finite lower bound and perhaps is representable as a sum or integral over some local densities in some appropriate space, such that which also will have lower bounds, such that we can quickly derive a Gibbs distribution for these densities, which takes care for an exponential rarity of rogue fluctuations in such systems, even if it's not a Hamiltonian one. And there are, of course, also bad systems, but I will not talk about them today and here. And pay attention also, please. I prefer the word sum here. I will talk about lattices, countable systems, and not about space continuous field theories. Right, so I want to somehow quantify thermalization, so I want to measure something. There are many ways you can do that. There are maybe two main ways how you can do that in classical systems. One goes via the notion of ergodicity, where you will define or choose or pick some observables of your choice. And then you will follow the fluctuations of these observables along some evolution of your system. And then you will measure their finite time averages. And you will try to identify those times at which these finite time averages start to become reasonably close to ensemble averages of the same observables. And then you have your timescales. You can see already there are lots of ambiguities in this approach. And this is what I was mainly presenting here 4 years ago. The other way is to go via mixing, that is simply measuring Lyapunov spectra, not just one largest Lyapunov exponent, but all of them. Then just invert them and get the Lyapunov times or Lyapunov time spectrum. That is rather clear, and you don't have to make any further assumptions. And I will follow this second path and show you results. So if we approach an integrable limit, it's clear that all these time scales must somehow diverge. And there might be other scales as well, which might diverge as well, similar almost to a phase transition, approaching it only from one side without the possibility to poke through and to go onto the other side. And then there are questions, how will they diverge? How many, or are they all diverging in the same way? How many different scales are there which are involved? Are there maybe different universality classes? May they probably come with critical exponents which we can compute, and so on and so forth. And before you will open or start to read in your laptops or in your phones, I will give you a nutshell summary. But I also promise you this shouldn't take too long, so it's not a 40-minute talk. So don't worry too much. So here's the nutshell summary. We did find two different classes of weak non-integrability of systems which slow down their thermalization in different ways upon approaching integrable limits. One comes under these three letters LRN, which stands for long-range network. And in that case, I'll tell more what that means. And in that case, there is one diverging timescale which will control all the other timescales of the thermalization dynamics. The second class which we found is a short-range network class. Here we have additional timescales or additional scales which are involved. And we find a dramatical slowing down of thermalization in that SRN short-range network class. Now, this is the only physics which I probably will bring in here. So just to give you a flavor on intuition, what these different classes may stand for. Long-range networks you will observe, so it seems, if you take a translation invariant system and you consider weak two-body interactions, which on a classical mean field level, say, will turn into weak nonlinearity. And in that case, why is it long range? Because when you come to the linear integrable limit, your eigenstates will be extended normal modes because of translation invariance. And when you add this weak two-body interaction, you will couple them all to all, essentially. And this is the long rangeness. So the long range or short range defines my network, which is spanned by the non-integrable perturbation between the actions or the map actions of the integrable limit. So the procedure is very simple. Go to the limit, find the actions, then go a bit back, add your non-integrable perturbation, and see what kind of network is it spanning among the actions. So then it's clear in the short-range network case, you will have only short-range couplings between the actions, and that's what is typically happening when you take a lattice version of such systems and you crank or you reduce the coupling on the lattice essentially down to zero, so you simply decouple all your lattice sides. You may still have some nonlinear evolution on each side, but you have, of course, an integrable system. And all I'm also assuming here is that this coupling, which you then add back, will be short-ranged. Right. So instead of now playing with Hamiltonian systems, we decided to immediately go into or to choose proper models from a unitary map toolbox, which many people are using, and we as well started to use in order to tackle problems which are seem to be at least computationally hard when you want to implement them with continuous time flows and Hamiltonian systems. And one example you see down here, this is a discrete time, so-called discrete time quantum walk model, which is a one-dimensional set of these two-level systems, if you wish. Then you add some periodic boundary conditions, but that doesn't matter so much. And the dynamics is very simple. You have, in one step, you first apply a local unitary to each of these two-level systems. So you basically just perform a rotation. On each of these sites, you have a complex scalar, a wave function if you want. And then in the second step, you will simply perform a shift operation, a register shift operation. So you shift all the plus values one step to the right and all the minus values one step to the left, and that's it. That's a very fast and efficient way how you can encode wave dynamics on a lattice. It is, of course, not a priori or clearly Hamiltonian, but it still conserves a norm, so it's a unitary macroscopic map. And such systems can be used, for instance, to study problems like wave packet spreading in disordered nonlinear systems. If you do that on with Hamiltonian settings, you will hit some threshold, some time threshold because of your CPU time, which is limited. If you realize the same problem using such unitary maps, turns out you can win 4 orders of magnitude in time and peak beyond the horizons which are set by your CPUs and your Hamiltonian dynamics. There are many other examples which are listed here where you can use these unitary maps to tackle computational hard problems, and I will now talk about these Lyapunov spectra. We thought that this is maybe a good idea because you not want to compute not just one Lyapunov exponent, but all of them, and you'll see there are, of course, lots of them. So in order to do that, we slightly modified our unitary map, or simply chose a slightly different one, which I will explain here again in a bit more detail. You see here again these sites. These were the previous pluses and minuses here, which I now just arrange in a linear fashion. And then you proceed with constructing your first unitary map, your first kick, so to say, your first step, by again applying a rotation or unitary transformation between nearest neighbor sites, yeah, in these pairs, with this matrix, which is parameterized by an angle theta, and which is more or less the analog of a hopping strength on a tight binding chain, for instance. Then, instead of doing these register shifts, you just do the same thing again, but you shift your yellow boxes by one side. And with that accomplished, you have done one step in your unitary map, in a linear unitary map. If you are now going to repeat that endlessly, you will again consider wave propagation in such a one-dimensional setting. Now, the nonlinearity is added. You can do that in different ways, but the simplest way is to add it locally to each site. You see these green boxes here. Each box is a very simple operation. You simply change the phase of each wave function in a way which is depending on the amplitude of the same wave function. And that's nothing but an implementation of a nonlinear unitary map. Yes, please. No, this is a nonlinear system, so there is no notion of single. So if I remove the green boxes, yes, then it's a linear map, and any linear evolution technically you can consider as a single particle. But I add nonlinear terms, and that makes everything different. That introduces chaos, positive Lyapunov exponents. So think about any nonlinear system. Would you call that a single particle problem? Yes. 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 Again, if I do not add nonlinear operations on these green sides, then yes. But if I do, then no. And you see here, this nonlinear action is parameterized by this little parameter, little g here. So if little g is 0, then yes. And if little g is non-zero, then you have some nonlinear evolution, unitary still, evolution. Unitary means that, of course, you conserve the total norm of the system. And that's what we are going to look at. This system is now expected to be non-integrable and still has two integrable limits. One we already discussed, g going to 0 or exactly equal to 0 brings you back to a linear unitary map. You can diagonalize this problem, find all the eigenmodes, and find that all the normal modes in that system conserve their respective norms. These will be your conserved quantities in that limit. The other limit is, yes? I'm sorry, I didn't understand your question. Repeat it again, please.
You have these two different setups here, like these networks. So like, how does varying theta move from like, or even G?
Okay, you
from
mean
this nearest neighbor hopping to this all-to-all connected setup?
Okay. You mean these two pictures here? That's art produced by Mitra Maleshava, and is a very artistic view. Okay, so you always deal with these systems. So basically what you have to think about that here you are working still in real space. This is more or less the same as what you see here. But here you first have to go into reciprocal Fourier normal mode space, Bloch space. You do a transformation from real space into Bloch space. And then you look again at the equations which couple the different variables, which are now the wave functions associated with each normal mode. I'll show you the equations a bit later. So this is just artistic, just indicating that there are two different limits in which you will find the system is the same in all your Crankes parameters, but in one case you enter a long-range network where the conserved actions at the limit are coupled long-range in a long-range way once you step a bit back from that integrable limit. That happens when G is small, but non-zero. And the other limit is short range, where you basically put theta to 0. When you put theta to 0, as you can see here, this becomes a unit matrix. So you decouple all the sides. But you still have these nonlinear things here, changing your angles. So what you will find if you add a small theta back into this game is that you obviously will couple these conserved quantities locally. And that's what is shown here in this artistic picture. Okay. Right. If you write down the equations, they look a bit ugly. This is how the map looks like. So all these psi's, n is the number of the unit cell, if you wish, and a and b distinguishes two different nearest neighbors. Psi n a at time t+1 and b at time t+1 equal to some crocodiles, which are functions of the psi's at time t. And there are also here these phase terms, which are written explicitly here, which again are also functions of the wave of the amplitudes at step time t. But what you can now do is you can take these equations and write them down close to these two integrable limits. So in the first case, we take the long-range network situation when G is small. So when G is small, you see we now transform first the problem into Fourier space. We go into K space. And then we write down the same equations in K space and add the smallest first term, non-zero term, which is linear in G, to, in the sense of a Taylor expansion, to the right-hand side. So this is how the equation look like now in this Fourier space for small g. So when g is equal to 0, you see you have an integrable system because c at time t plus 1 is equal to c at time t up to a phase vector. So you conserve the norm of each normal mode. But when you add a non-zero small g, you get all these right-hand side terms, a huge number of them, which is a sum over things here, including products of 3 in general different normal mode wave functions. And this proliferating number of terms on the right-hand side tells you that basically, even when g is very small, any normal mode is coupled to practically all the other normal modes through these terms here on the right-hand side. And that's what is meant, loosely speaking, by long-range network. One can quantify these long-rangeness in a better way, but I won't do that here right now. On the other side, if you take the short-range network, that is, you consider small theta, then you again expand the equations to leading order in small theta, and this is what you get. When theta is equal to 0, remove these terms, and you see, of course, that you have now that you now preserve the norm on each side for all times. So now your conserved quantities are the local norms on each side. And when you add a small theta, you couple them in a short range way to their nearest neighbors. That's all. Okay, with that said, now let me say what I mean by and how we compute Lyapunov spectra. So there are, Lyapunov exponents, as you maybe remember, characterize exponential growth of small fluctuations. And the number of Lyapunov exponents strictly equals the phase space dimension. And this is true also for these unitary maps. And the phase space dimension is basically just the number of these, 2 times the number of the psi's you have to deal with in this problem. And they do come also in pairs of plus and minus lambda. So to each positive Lyapunov exponent, you have a corresponding negative one. This is because the map is unitary. And per each integral of motion, you must have exactly 2 zero Lyapunov exponents, therefore. And if you want to learn how to compute them numerically on your computer, which is much less horrible than it maybe seems at the first glance, you can, for instance, go to this old paper by Benetin, Galgani, Giorgilli, and Stelzin, but you can maybe also find other resources which will tell you how to do it. It's very simple at the end of the day. Let me give you a flavor what and how we do it in this case of these unitary maps here. So we initialize some state, typically with random local phases and a non-zero, on average, a non-zero norm density in our unitary map system, which we distribute according to some Gibbs distribution initially, and then we just run the trajectory as long as we can. Then we add a small perturbation, and then we linearize the map equations actually on paper, and we write down a tangent map, and then we propagate this tangent map again numerically. And if we were to do only that, we would now compute the largest Lyapunov exponent by simply following a small perturbation in this tangent map. It should grow exponentially in time. And the fastest growth is given by the largest Lyapunov exponent. And then what you do is you measure the exponent of this growth and you average it over time. And when this averaging quantity saturates, you measure it off and say, this is my largest Lyapunov exponent, which is very interesting because when you measure Lyapunov exponents, you actually average observables. You compute finite time averages of observables, which means there must be some phase space averaging analog to compute Lyapunov exponents. Right, but we want to compute more than just one Lyapunov exponent, so we write more than one tangent map simply. We write actually 2 times n tangent maps, where n was the number of sites in our problem. And then tangent map number 1 will give us the largest Lyapunov exponent. And in tangent map number 2, we will project our perturbation perpendicular to the one from TM1, and therefore we will get the second largest Lyapunov exponent by again doing an averaging of the exponential growth of its vector, and so on. And that's how we compute all of the positive and all of the negative Lyapunov exponents. We can check whether they come in pairs, everything. And then they also come already sorted by this principle. We will finally only look at the positive ones. And the lambda 1 is the largest Lyapunov exponent. And instead of then looking at all the others, what we will do is we pack them together in this V-scaled spectrum. So we have lambda bar, which is any other Lyapunov exponent divided by the largest. And it depends now on rho, which is the original index, sorting index, divided by the volume of the system. So this is a nice spectrum, which always has to start at 1 for rho equals 0, and then it has to decay to 0 at rho equal 1. Okay, so now then you switch on your computer and run it. And after you removed all the bugs, or if you think that you did remove all the bugs, this is what you probably will see. These are some raw, yes. We simulate the full trajectory. Okay, the question was whether we simulate the full system or the perturbations, both. We simulate the full trajectory, and then we run also all these tangent maps, because they have on input numbers which come from the trajectory. They are not independent.
So the perturbation is well defined, you say?
Yes.
Okay.
Okay, so this is how the raw data look like. Let's take the top of this bunch of lines here. This is the largest Lyapunov exponent, or this is the quantity which you average over time. This is a log of time here, goes until say 10 to the 7. And so you see something coming down, and then it saturates. And when this observable saturates, you read it off and say, that's my largest Lyapunov exponent. And then there are all the others, which you can see here. They saturate at later times, because they usually saturate at a time which is roughly proportional to the inverse of their own. There's a very interesting observable, quite unique compared to other ones. And then there is one of them which hopefully will continue to decay down to 0, because we know, or we think we know, that there must be at least one Lyapunov exponent from the positive side, which has to be actually 0. And then there must be, of course, another one from the negative side, which has to be 0 as well. Right, so now, after you've done that, you can, for instance, look at the largest Lyapunov exponent, lambda max, or lambda 1, and look how it depends on the distance from the integrable limit. Well, you don't see much interesting, all expected. Long-range network means G is cranked down to small values. Largest Lyapunov exponent seems to go down. This is log-log, probably in a power law way. You might now try to read off some exponent and try to make your theory on that. But otherwise, it's just doing the expected thing, going down to 0. So you see a slowing down of thermalization. Pay attention, the largest Lyapunov exponent is the largest. So its inverse is what we say call the Lyapunov time is the shortest time. So if that time diverges, all the other times, of course, diverge as well. In the short range network case, when we tune the coupling between the sides to 0 by tuning theta to 0, we see more or less the same thing. Maybe there's a different exponent, but that's all to it. Okay. But if we now look at what the other Lyapunov exponents are doing, things get interesting. So for the long range network, which is again the limit of small nonlinearities, G going to 0, you see here more or less, well, not all of them, but some of them as a function of G. And on a log-log plot, you see here's the largest Lyapunov exponent, which does just what we have seen on the previous slide. And then come all the others, which seem to do more or less the same thing, just shifted in a parallel way. which means that if you know one of them, you can tell what all the others are, right? They are all proportional to each other. Indeed, if you look at the rescaled spectrum lambda bar as a function of rho, remember this thing has to start at 1 at rho equals 0 and then decay to 0 at rho equal 1. At any distance from the integrable limit, you will typically see some nice smooth curve like this one. And then as you come closer to the integrable limit, this curve somehow changes, bends a bit or whatever it does. But then finally it freezes on this, say, dashed line which you see here. And that means that infinitesimally close to the integrable limit, probably, because we can't go there computationally, the rescaled Lyapunov spectrum will stay an analytic function, which tells you if you know one Lyapunov exponent, you know them all. If you know one time, you know them all. So that's the outcome of the long-range network. But in the short-range network, things are different. Again, you see here the Lyapunov exponents versus the parameter theta. Theta going to 0 brings you to the limit of disconnected sides. You see here the largest Lyapunov exponent, and then you see the other ones, and you see they don't follow in parallel ways, but you see some kind of fan opening. So there is something going on, and you can understand it better by looking at the rescaled spectrum. Again, if you look at lambda bar as a function of rho, you see that these smooth curves which you obtain are bending, but they never stop bending. Basically, they just seem to tend to a non-analytic trivial function, 1 at 0 and 0 everywhere else. But if you plot the same rescaled spectrum on a logarithmic scale, what you find is that it actually decays exponentially versus rho, and that this exponent diverges as you approach the integrable limit. So there you go. You find, if you wish, a second diverging scale, which is this related to this exponent. Or if you wish, you find that all the other Lyapunov exponents or all the other corresponding times, which are the inverses of those, all these times become much faster, larger than the time which corresponds to the largest Lyapunov exponent. So you see some kind of freezing of parts of the system, although the system probably on large enough times is still ergodic. Okay. Then you can play around and do fittings and convince yourself that this is, find, so to say, quantitative ways to which support your findings. Maybe I should just mention one, which is this Kolmogorov-Sinai entropy and its rescaled KS entropy density version, which is actually nothing but the integral under one of these curves here. So if you compute this integral, then you indeed find that in the long-range network case, this integral tends to some finite value at the integrable limit, which means that your rescaled spectrum indeed saturates on some invariant curve, while the short-range network gives you a 0, which means that your rescaled spectrum essentially becomes a non-analytic function. Right, you can do more things, and maybe I should not, more tests, I should not go into them, but just mention that you can also add disorder. And for instance, in this linear version of these unitary maps, if you add disorder in a proper way, what you can do is you can arrange all your eigenstates to be Anderson localized with one and the same localization length, which you can control by one parameter, namely this, this angle theta, so that you can vary your localization lengths between 0 and infinity. That's aesthetically very nice. You have a system where you have disorder, all eigenstates are localized, all with the same length, localization length, and you have a parameter which you can use to tune it, and you have even a formula which you can use. So, but now if you take such a system and now you add again, let's say weak nonlinear terms, then things will be different. Remember, we discussed that our unitary map is translation invariant, and therefore at G equals 0, this linear unitary map has eigenstates which are kind of normal modes and extended over the entire system. But if you now have disorder, they will be localized, Anderson localized, only extended over a finite part of the system. And therefore, these, let me just show them again. Oops, it was longer than I thought, sorry for that. And therefore, these terms here on the right-hand side will not proliferate with the volume of the system, but stay finite, because only a finite number of other modes will be coupled, Anderson modes will be coupled to a given Anderson mode. And then you can use that case for a finite system and now change the localization lengths and see how you cross over from say a long-range network regime into a short-range network regime upon reducing the localization length psi. So there are many other things you can do, but time is up. So let me just give you some take-home messages. We did observe two distinct universality classes of thermalization slowing down in macroscopic systems. And the classifier here is the network type, which is spanned by the non-integrable perturbation over the actions of the integrable limit. In the long-range case, we have essentially an all-to-all coupling, and as a result, we have one timescale, thermalization timescale, which controls all the others. In the short-range network case, things are more complicated, and we have at least two scales, one time scale and probably one length scale, but that is something which I didn't have time to discuss. And if you add disorder, you may observe in finite systems a transition from long range to short range. And this works equally well for also Hamiltonian continuous time flows. And in particular, it works equally well in any dimension. So as far as we can tell, 1, 2, and 3 dimensions, there's work in progress, and archives should be appearing soon. And finally, just allow me to say mention a few open issues. Naturally, are there more classes? Well, I'm not even mentioning the problem of finding better theories to explain everything. But also, are there interesting other integrable limits? There are models we know which are integrable, the Toda lattice, for instance, the Ablovitz-Ladek lattice, or the ideal gas, or many others. And finally, even the weak discretization of time flows itself, which can act as a non-integrable perturbation if you try to integrate, let's say, a time continuous system, which is supposed to be integrable. And with that, I thank you very much for your attention.
Thanks for the nice talk. We have time for a few questions.
Thank you. So I may have missed it. What is the number of local degrees of freedom on each side?
So on each side, you have one complex scalar, so it's 1 degree of freedom.
Okay, and then my question is, so your integrable case was actually a free theory. Could you also try this with an interacting, say, integrable model?
By interacting, yes, okay, so let's stay classical. And then I guess that by interacting, you mean nonlinear.
Yeah.
Okay, then we take Toda, for instance, or Ablovitz-Ladek.
Okay.
Toda lattice is a nonlinear lattice, which is integrable. Ablovitz-Ladek is a version of a discrete nonlinear Schrödinger equation, which is integrable, and there are others. Yes, I think one can do it. We didn't so far.
Do you expect the same thing to happen?
The good, yes and no. I think yes, but the question is, what's the network type? And that I don't know, because if I want to know the network type, I have to take Toda, write down all the actions, all the integrals of motion and their actions, and then I have to write down and then I have to see what my network will be, which is spanned by some non-integrable perturbation.
I have some other questions, but I don't want to.
And I don't know how to do that, but yeah.
Thank you. Thank you.
The questions?
Yeah, so I mean, apart from looking at the Lyapunov spectrum, I mean, so how exactly would you define thermalization in this problem, and how does the spectrum actually affect thermalization? Because usually, I mean, one talks of the largest Lyapunov exponent and tries to relate it to thermalization. But
well, that certainly doesn't work in general. Yes. So, yeah, that's getting philosophical. That's what I try to say. Instead of saying that I have now a time scale on which we can consider that our system thermalizes, I just produce all these Lyapunov timescales and say, then do with them what you want. So technically speaking, there's always one smallest positive one, which can be as small as you wish in a system which I can choose as big as I want. And then we probably would have to wait until this astronomical timescale if we want to wait until all finite timescales were reached. So things are complicated. Let me show you again this one of these.
does it affect things like when I take time average of some observable? And does this smallest
Beautiful question. So look, so now you can do the following. If you do if you follow the ergodicity path, you have to choose your observable. Which one? Well, if I talked about this 4 years ago, and then I was trying to convince you that if I ask this question about approaching an integrable limit, of course, I will look at my actions, which are the frozen quantities at the integrable limit. And those things start to slowly fluctuate as I depart, and I will study them. But you may say, no, I don't want to study them. I want to study, for instance, a huge system, and then I take 1/2 of it, and I measure the whatever norm or energy in that half, and I ask, when is this thing going to the time average of this observable going to reach its phase space average? And these are probably observables which are related to these extremely small Lyapunov exponents here, which you always have in any system. So any system gives you, let's say, such a curve. At some finite distance, you're not even close to an integrable limit. You're somewhere, you're happy. All parameters of order 1, you get this line. What does it mean? In your computer, you have a finite system, so you basically just have, you grid this curve with points, okay? But there's always the smallest point here, which is somewhere pretty close to 0, not exactly at 0, but close to 0. But if you now increase your system, you can make, this point will drift further and further closer to 0. So if I make my system big enough, I make my, my thermalization time, which I want to relate for some reason with this smallest positive Lyapunov exponent, arbitrarily big. And that means nothing thermalizes, which of course is maybe not the right way, some people would argue. And so therefore I'm saying that's philosophical. That's where, I'm just reporting on these spectra, and then probably at this time we should say that please use them at your discretion, but I don't, and we can discuss later what that means and what means thermalization in a closed conservative system in the first place.
I'll ask a question. So at the start of the talk, you said you'd be willing to speculate on how these results might extend to truly quantum models.
Right.
So curious to hear about that.
Yeah. So if so, my take on that is, if we look at all the systems which seem to fall into this short-range network class, once you quantize them, you end up with models which are beloved, most of the time beloved, models for computational physicists to study many body localization. And if you take the long-range network classes, they for some reason are not the beloved models. So I think there might be some reason to assume that if you quantize short-range network systems, you will see a dramatical further slowing down of thermalization, perhaps down to no thermalization at all, while in the long-range network case, things will do go a different path.
I like this idea of two new universality classes, beloved models and not loved models. So that will stick with me. Do we have any more questions for Sergej? If not, let's thank him for a nice
Thank you.
talk.